Hello everyone. Today we will be studying the polarization of light part 2. The first part of the video is already there in YouTube and you should get the link in the description box of this video. So let us first do some recap what we did in part 1, that there was polarization of light, that is what is polarization, what is unpolarized light, what is polarized light. Then we did some application of polarization of light. Then the main part was the different ways to produce polarized light, like reflection, refraction, double refraction and scattering. And finally we did some little bit discussion about different states of polarization or different states of polarized light. In today's lecture we will mainly discuss about the production of different polarized light and the detection of different polarized light. For this purpose we need to revisit double refraction a bit. Then we will study different types of crystals which produce such double refraction, and finally we will study about optical activity. So let us discuss about double refraction. You know that in double refraction, the name says it all. We get two refracted beams from one beam. Here you can see that we have an unpolarized incident beam which falls on some crystal, and we are getting two refracted beams. The main important thing is here that the two refracted beams are both plane polarized, but their plane of vibrations are mutually perpendicular to each other. So in case of double refraction we get to see two images like this. In this figure I am watching a line through a calcite crystal, and here you can see that there are two lines. So this is property of some specific anisotropic crystals. Those crystals are known as birefringent crystals or doubly refracting crystals. So when an unpolarized light falls on such a crystal, it gets refracted into two beams. They are called E ray, stands for extraordinary ray, and O ray, stands for ordinary ray. The difference between them is that the ordinary ray, it follows the Snell's law, whereas the extraordinary ray does not follow any Snell's law. The vibration of the E ray is parallel to the plane of the board, whereas the vibration of the O ray is perpendicular to the plane of the board, which you can see from this image. Now, such doubly refracting crystals can be classified into two categories: positive crystals and negative crystals. So in the last slide we discussed about E ray and O ray, and I said that E ray does not follow Snell's law. What do you mean by that? O ray is ordinary ray, means it will move along any direction with same velocity. As a result of it, you can see that the wavefront of the O ray is spherical. Okay. So as O ray travels along all the directions with same velocity, the wavefront is spherical, but E ray does not do so. The velocity of E ray depends on the material of the crystal, and as a result of it, E ray moves with different velocity along different directions inside such anisotropic crystals. As a result of it, the wavefront of the E ray, given by the dotted line here, is elliptical. Now, we classify the anisotropic crystals according to the velocity of O ray and E ray inside these crystals. If the velocity of O ray is greater than the velocity of E ray in any crystal, that crystal is known as positive crystal, and vice versa. That is, if the velocity of O ray is less than the velocity of E ray, the crystal will be called a negative crystal. Calcite is such negative crystal, whereas quartz is an example of positive crystal. And as you can see from the picture that the sphere is inside the ellipse in this case, which means that the velocity of O ray will always be less than the velocity of E ray in negative crystal. And in this picture, the ellipse is inside the circle, which means that the velocity of E ray is always less than the velocity of O ray for the positive crystal. If you look carefully, you can see that at these 2 points, here and here, in case of this picture, here and here, at these 2 points, the ellipse and the sphere touch each other. It means that along this particular direction, E ray and O ray have the same velocity. So every crystal must have at least one such direction where the E ray and O ray will have the same velocity. That particular direction is called as the optic axis of the crystal. So the crystals having only one optic axis is known as uniaxial crystal. The crystals having more than two optic axes are known as biaxial crystals, etc. Now, so this was about E ray and O ray, and depending on positive or negative crystal, either velocity of O ray will be greater or velocity of E ray will be greater. The main thing is that apart from the optic axis, in any direction if the light goes, the E ray and O ray will travel with different velocity. Now, what happens if a plane polarized light passes through such birefringent crystals? Will birefringence take place? The answer is yes. Here you can see a plane polarized light falls on a calcite crystal. I have drawn the vibrations like this to indicate that they make an angle with the axis. Now, when they fall on the crystal, they will again doubly refract into two plane polarized light. One will be parallel to the principal section of the crystal. So let me draw this parallelepiped. So the principal section of the crystal, let us say, is on the plane of the board. So the E ray must have vibrations parallel to the plane of the board, that is parallel to the principal section of the crystal. That is, E ray is vibrating like this, whereas the O ray, as you can see that the O ray is vibrating perpendicular to the plane of the board. So O rays have vibrations perpendicular to the principal section of the crystal. So when a plane polarized light falls on a doubly refracting crystal, we again get two plane polarized rays moving along the same direction, but they are having mutually perpendicular electric field vibration direction. Okay, now this thing we need in order to produce different types of polarized lights. So what are the different types of polarized light? It was also discussed in the last lecture. So there are basically three types of polarized light: linearly or plane polarized light, elliptically polarized light, and circularly polarized light. In case of linear polarization, the electric field vector, this one, the orange one, okay, the electric field vector, it vibrates along a line. Okay, so it will be like this. As it moves on, the direction will be same, but the magnitude will vary from 0 to maximum. So that is linearly polarized light. In case of elliptically polarized light, as the light moves along this direction, the tip of the electric field vector, this one, it will rotate along the ellipse. The tip of the electric field vector will rotate along the ellipse. This is called elliptically polarized light. Circularly polarized light is a special case of elliptically polarized light, where the tip of the electric field vector, it rotates along the circle as the light travels. Okay. Now how are they produced? They are produced by superposition of two plane polarized lights having mutually perpendicular plane of vibration moving along the same direction. Now they result in linear, elliptical or circularly polarized light depending on the amplitude and the phase shift between the two waves. So this is the important factor, amplitude and phase shift. It will decide whether the light will convert to plane polarized or elliptically polarized or circularly polarized light. How it does that? Let us check. So suppose a plane polarized monochromatic light is incident normally on a calcite plate with faces cut parallel to the optic axis. This term is very important. Faces cut parallel to the optic axis. Now, for example, let us say it's a calcite crystal, okay? And let me say that this axis, the length one, is the optic axis of the crystal. Now, let this be our incident ray. Incident ray is falling on the calcite crystal, where the optic axis is parallel to the refracting surface. This is the optic axis. It is parallel to the refracting surface of the crystal, and light is incident like this. So optic axis and incident light, they are mutually perpendicular, as you can see from this picture. The light falls on a surface where the surface contains the optic axis and light is moving along perpendicular direction of the optic axis. So what will happen? Whenever light moves along any direction apart from the optic axis, we get double refraction or birefringence. So as a result of it, we get two plane polarized lights, E ray and O ray. And you know that when any two ray travel with different velocity along the same direction, after going about some length, it will develop a path difference between them, or as a result of it, we will get a phase difference between the E ray and O ray. As you can see in this picture, so let me say that the optic axis is this, that is optic axis along the x-axis. So x-axis must be this, that is perpendicular to the plane of the board. Y-axis is vertical and z-axis is this. So this is y, this is x, this is z. Now in this picture we have plotted x along this direction, z along this direction, and y is perpendicular to the plane of the board in this picture. So as a result of it, you can see that the optic axis is along the x-axis and the wave moves along the z-axis. So this will, the incident plane polarized light, it will be having two components, one parallel to the optic axis, the other one perpendicular to the optic axis. The ray which is parallel to the optic axis will be called E ray. The ray which is perpendicular to the optic axis, given by the dot, is called the O ray. So on entering the crystal with amplitude A, the vibration may be assumed to be resolved into two components. the E ray vibration parallel to the optic axis. So the amplitude can be given as small a equal to a cos theta, and the O ray with vibration perpendicular to the optic axis, the amplitude can be given as small b equal to capital A sin theta. So this is small b, this is small a. Okay, that is on entering the crystal with amplitude A. What happens when they emerge from it? So again I have drawn that picture from the earlier slide. So this is small a, this is small b, and this is the x-axis, the optic axis. So let the incident wave has the equation E equal to capital A cos omega t minus kz. Denotes that the wave is moving along the z-axis. So the components wave initially will be given by x equal to small a cos omega t minus kz and y equal to small b cos omega t minus kz. Here you can see that small a and small b are used, where small a is a cos theta and small b is capital A sin theta. So it also denotes that the two component waves, they are moving along the z-axis, because in cos term we have minus kz, but here we have x equal to a cos omega t minus kz, here we have y equal to b cos omega t minus kz, indicating that the first one, the vibration is along the x-axis, whereas for the second one the vibration is along the y-axis. So this is the equation for E ray and this is the equation for O ray. Okay, so this was initially. Now as the two rays travel with different velocity along the crystal for a certain width, as you can see that this was our incident ray, and the ray will be divided into two parts and they will travel this much amount of length together, and while moving through the crystal they will develop a path difference, and as a result of it they will develop a phase difference, and thus the component wave equation after passing through the crystal will change to a equal to a cos omega t minus kz plus delta, where y equal to, we have kept it same, b cos omega t minus kz, where this delta is the phase difference. So delta is the phase difference between O ray and E ray. Now we have got two equations, and from here simply using algebra we can get x by a equal to cos omega t minus kz plus delta and y by b equal to cos omega t minus kz. Now we will use this x by a and we will expand the cos term, that is cos a plus b equal to cos a cos b minus sin a sin b, in such a way. And after doing some algebraic as well as trigonometric equations, we will be getting this result, that we have the equation x square by a square plus y square by b square minus 2xyab cos delta equal to sin square delta, which is a general equation of an ellipse confined to a rectangle of sides 2a and 2b. Now you can see that the equation will vary as delta is changed. So let us see what happens for different delta values. So let us say delta is given by case 1. Case 1 delta is 2n pi, where n is any integer 0, 1, 2, 3 etc. So if delta is 2n pi, we have cos delta equal to 1 and sin delta equal to 0. So the equation will be x square by a square plus y square by b square minus 2xy by ab equal to 0. From here we get the equation y equal to b by a into x, that is y equal to mx plus c, the equation of a straight line passing through the origin with the slope b by a. So if we get a relation between x and y like this, So we can say that the emergent light is also plane polarized. As you can see that the electric field is vibrating only along a line. Okay, so we get plane polarized light if delta equal to 2n pi. The next case, delta equal to 2n plus 1 into pi, that is odd multiple of pi. The first one was even multiple of pi, next one is odd multiple of pi. What will happen? Cos delta term will become minus 1 and sin square delta will be 0. So the equation will reduce to x square by a square plus y square by b square plus 2xy by ab, this one, equal to 0, and from here we get an equation like y equal to minus b by a into x. Again we get an equation of straight line, but this time the slope is negative. It is given by minus b by a. So straight line passing through the origin with negative slope, this one. So what type of light is it? Yes, it is a plane polarized light, but you can see that the vibration state has changed. From this earlier, the vibration is now like this. So again we are getting a plane polarized light but with a different vibration. Moving on to case 3, where delta is given by 2n plus 1 into pi by 2, n being 0, 1, 2, that is odd multiple of pi by 2. What happens then? If this is odd multiple of pi by 2, cos delta will be 0 and sin delta will be plus 1 or minus 1, or sin square delta will be 1. Simply we get x square by a square plus y square by b square equal to 1, which is equation of an ellipse with semi-major and semi-minor axis as a and b. So you can see that we get a circularly polarized light as, we get a elliptically polarized light as it is an equation of an ellipse. Case 4, again we said that circularly polarized light is a special case of elliptically polarized light. So we get the same condition first, that is delta equal to odd multiple of pi by 2, but along with it we have some other condition, that is a equal to b. So what was a? Small a was capital A cos theta and small b, it was capital A sin theta. So if a equal to b, we must have theta equal to 45 degree. So if the incident rays vibration is at 45 degree with the optic axis of the crystal, we get the initial amplitudes to be same, and as a result of it, the equation, the general equation is reduced to x square plus y square equal to a square, which is the equation of a circle with radius a. Thus we get circularly polarized light by superposition of two plane polarized light having vibration perpendicular to each other, and theta is given by 45 degree. Now circularly polarized light can be classified into two types of light: right circularly polarized light and left circularly polarized light. Right circular means it will move like this, that is clockwise. In case of left circularly polarized light, the movement will be anti-clockwise. So generally for delta equal to pi by 2, 5 pi by 2, that is 90 degree, then 540 degree, we get right circularly polarized light. For left circularly polarized light, delta will be minus 90 degree. Minus 90 degree can be represented by 3 pi by 2. So delta 3 pi by 2, 7 pi by 2 gives us left circularly polarized light. Thus by superposition of different plane polarized light, we find or we can generate different states of polarized light. Now, retardation plate. It is an optical device which can change the state of polarized light. That is, it can convert plain polarized light to circularly or elliptically polarized light, or elliptically polarized light to plane polarized light. It can convert right circularly polarized light to left circularly polarized light. Whatever it does, it changes the state of polarization of a light. But retardation plate cannot polarize any unpolarized light. You have to keep this thing in mind, that it cannot produce a polarized light from unpolarized light, but given a polarized light, certain type of polarized light, it can easily change the state of polarization. So there are two common types of retardation plates. One is called the quarter wave plate, another one is called the half wave plate. Quarter wave, quarter means 1/4. So quarter wave plate is such a device which can convert linearly polarized light into circularly or elliptically polarized light by introducing a path difference of lambda by 4. If you remember, we can get elliptically or circularly polarized light from plane polarized light. Let me show you. If delta is 2n plus 1 pi by 2, that is odd multiple of pi by 2. So minimum will be pi by 2, minimum phase difference. So pi by 2 phase difference corresponds to path difference of lambda by 4. So that is why the quarter wave plate, it can convert linearly polarized light into elliptically polarized light by introducing a path difference of lambda by 4. Now, how to produce such quarter wave plates? So we have to take some birefringent crystal and make a parallelepiped type of shape from it with a specific width. The width is given by d. So how do we calculate d? The optical path difference between the rays after traveling through the crystal of length or of thickness d is given by d into mu o difference mu e. We have written here difference, not minus, because we don't know which one is greater, mu o or mu e, because depending on positive and negative crystal, any one can be greater. So it is only difference. So d into mu, that is geometrical length multiplied by refractive index, gives you the optical length. So the optical path difference will be given by d mu o difference mu e. So this optical path difference should be equal to lambda by 4 for quarter wave plate. So from here we can get d equal to lambda by 4 into mu o difference mu e. Similarly, half wave plate, the name suggests that it will introduce a phase difference of half of 2 pi, that is pi, or path difference of lambda by 2. So what does the half wave plate do? By introducing a path difference of lambda by 2, it shifts the polarization direction for linearly polarized light, or it can change left circularly light to right circularly polarized light, or vice versa. So the optical path difference for half wave plate again will be d equal to, again it will be d into mu o difference mu e, and in this case d into mu o difference mu e must be equal to lambda by 2. So the thickness for a half wave plate must be lambda by 2 into mu o difference mu e. Thus we can change the state of polarization by using retardation plates. We will need this retardation plate later while detecting different types of polarized light. Okay, so first in the detection comes the plane polarized light. So as you can see that plane polarized light falls on a nickel prism, which is an analyzer, and so let us say this be the incident plane polarized light, and this is our analyzer, where the length, it is the axis of the analyzer, and let this be the direction of polarization or the direction of vibration of the polarized light. So this one, it looks like this, and the length, along the length we will have the axis of the crystal. Now when the length is parallel to the axis, or when the axis of the crystal is parallel to the vibration direction, according to Malus law, the whole intensity will be transferred. But when they make a 90-degree angle, that is the axis of the crystal and the vibration of the plane polarized light, if the angle is 90 degree between them, the whole intensity will be blocked and we will get zero intensity of the emitted light. Okay, so look at this picture. The blue arrows, they denote the vibration of the electric field. So here in this one, the axis of the crystal is perpendicular to the vibration of the electric field, so the whole intensity will be blocked if light is coming in this way. But if we rotate it and make it like this figure, if we rotate it and make it like this, we will have the whole intensity passing through the crystal. As a result of it, for a 360-degree rotation, that is, let us have the electric field like this. So for this position we will get a maxima, in this position we will get a zero intensity, again in this position we will get another maxima, and again in this position we will get another zero. So for a 360-degree rotation of the crystal, we are getting two positions for maximum intensity, two positions for zero intensity in case of plane polarized light. So if you look at the plane polarized light, light is coming towards me and I am looking through it. So for a 360-degree rotation we get two maxima and two zero minima. What happens for elliptically polarized light? As you can see that in case of elliptically polarized light, the electric field vector strip moves along an ellipse. So when the axis is parallel to the semi-major axis, we get the maximum intensity, and as you go on rotating the crystal, the intensity decreases, and at this point, when the axis of the crystal is parallel to the semi-minor axis, we get minimum intensity. But the difference between elliptically and plane polarized light is that this minimum is not zero, so we get a non-zero minimum intensity here. Again, as we go on rotating the crystal, again at this position we get that highest intensity which we got earlier, 180 degree earlier. Again rotated by 90 degree, we get minimum intensity, non-zero minimum. So for a full 360 degree rotation of the crystal, we get two position for maximum intensity, two position for non-zero minimum intensity in case of elliptically polarized light. Okay. What happens for circularly polarized light? In case of circularly polarized light, the tip of the electric field moves along a circle. So wherever I keep this crystal at whatever orientation, I will always get the same intensity. So uniform illumination for a 360-degree rotation of the nickel prism or the analyzer. If you remember, what happens for unpolarized light? What was unpolarized light? The electric field vectors were randomly oriented in the perpendicular plane of the light ray. What will happen in this case? Wherever you keep the analyzer, you will be getting the same intensity. So using only one analyzer or one nickel prism, we will be getting the same result for unpolarized light and circularly polarized light. So it is not possible to differentiate between them using only one analyzer. For that, we need something else. What? We need a retardation plate. Remember what was retardation plate? It was an optical device which can introduce a path difference between the O ray and E ray to change the state of polarization of light, but it cannot produce polarized beam from unpolarized light. So when we pass a circularly polarized light through a quarter wave plate, so for the detection we will use a combination of quarter wave plate and an analyzer. Okay, so when circularly polarized light is passed through a quarter wave plate, it converts into plane polarized light. But when unpolarized light passes through a quarter wave plate, it does not convert into any type of polarized light, it remains unpolarized. Now what do you have in the second phase? You have one plane polarized light, one unpolarized light. Now if you pass this polarized light, plane polarized light through an analyzer and rotate the analyzer 360 degree, what are you getting? Again you get two position for maxima and two position for zero minima. But if you pass the unpolarized light through the nickel prism and rotate the nickel prism or analyzer through 360 degree, you will be getting uniform illumination. So in case of circularly polarized light using quarter wave plate and analyzer, we get 2 maxima to 0 minima. In case of unpolarized light, after using quarter wave plate and nickel prism, we get uniform illumination. Thus, we can differentiate between circularly polarized light and unpolarized light using these two devices. Now, there are special substances which are able to rotate the plane of polarization of a plane polarized light. Such substances are called optically active substances, and the phenomena is known as optical activity or rotatory polarization. So they can change the vibration direction. So if some substance changes the vibration direction like this, that is, they rotate the electric fields clockwise or in the right direction, they are called dextrorotatory substances. Example is glucose. Similarly, some substances, they rotate the vibration direction in the left hand direction or anti-clockwise. They are known as levorotatory. Example is fructose. Bio observed some rules that these are not haphazard. The rotation depends on first the wavelength of the light. The rotation is proportional to 1 by lambda square, lambda being the wavelength of the light. Thus you can see that for violet ray, the rotation is greater than the red one. Now, if the wavelength and temperature remains same, then for a given wavelength, theta, the rotation, it is proportional to the length of the substance. So theta is proportional to L and theta is proportional to C, where C is the concentration of the solution. Suppose we are using a sugar solution. So take a sugar in a beaker with some water, and as you increase the concentration, if you do the experiment, you will see that the theta, the angle of rotation, is directly proportional to C and theta is directly proportional to L, and together we can write that theta equal to SLC or S equal to theta by LC, where this S is called the specific rotation of the substance. So if L and C are 1 and 1, S equal to theta. So for a given temperature and wavelength, remember that this must be constant, temperature and wavelength. So for a constant temperature and wavelength, the specific rotation is the rotation in degrees produced by 1 decimeter length of the substance in solution when the concentration is 1 gram per cc. So that is by convention, the definition is like that. We have to take 1 decimeter length. So thus we can get the specific rotation of different substances. So that was all from the polarization of light. Thank you.